Okay, so hello everyone, and thank you so much for joining us. My name is Katrina. I'm the machine learning math lead here at Cohere Labs, and today we're really excited to invite our guest speaker, Luis. He's currently a master's student in computer science at UNICAMP, Brazil, and today he's going to be sharing with us one of his main research projects. And with that, I'll give it over to Luis, and thank you all so much for joining us today.
Okay, thank you, Katrina, and thank you for Cohere Labs for the opportunity, and thank you for everyone for joining. Basically, I have a short presentation here. I want to share with you my research project. I developed this research during my internship in Canada. As I mentioned to Katrina, I went to Canada 2 months ago. I did an internship at Concord University, and basically I worked in an autonomous vehicle lab. It was very interesting, and yeah, in this presentation I want to share with you our results, and that's great. If you have any questions, like feel free for interrupt me. Or at the final of the presentation, have a question answer session. Okay, so my name is Luis. I'm Peruvian, but right now I'm doing my master's in Concord in UNICAMP, Brazil. I'm master student here, and also I'm PyTorch Ambassador in 2026. Basically, I like to share my knowledge in a community and my projects, and really like that. The research project that I'm very interested in is NLP, foundational models, large language models, in federated learning scenarios. So basically, in this presentation, I want to share our research project, which started efficient to the LiDAR as an understanding for autonomous driving via multimodal self-supervised learning. This research was developed in a Concord University, as I mentioned, together with Professor Aziz Shadi. It was an interesting experience working with Professor Shadi. Yeah, basically, I want to share a problem definition, related works, research proposal, objectives, the methodology, and the results. Our research is in a self-supervised learning area and in an autonomous vehicles field. Okay, so basically, for give a little bit context here. One of the major challenges in autonomous vehicles is collision detection. Basically, there are a lot of companies of autonomous vehicles in the world who's working with prevent more accurate these kind of problems for avoid accidents, etc. So for achieve this objective, basically a lot of researchers is focusing work. Basically, they capture a different kind of data from vehicles, autonomous vehicles, using different kind of sensors, different kind of cameras, proximity sensors, etc. And they collect this different kind of data to train models and try to measure, try to predict collisions, avoid collisions, etc. So one of the classical applications is using, for example, images. Like there are a lot of research about that, basically for try to predict, for example, the collisions between cars using an image data. In this case, for example, there are a lot of research in this area, but what happens, for example, if we want to add more data for trying this kind of models? In this case, for example, we don't just use images. We can use, for example, LiDAR data. LiDAR data from the LiDAR sensor, the car. So in this case, we need to add another sensors, another type of data. But the principal challenge here, for example, is how we can synchronize this kind of different types, data types. For example, how can we synchronize the image to correspond to LiDAR data? For try to measure more accurate, for example, the distance between the ego vehicle to another objects, for example, to the car. So in this case, for example, in this research, just using images to measure the distance and try to set, for example, a threshold and try to decide if the car will be, if we will be occur a collision or no. Here, for example, we can measure more accurate using LiDAR data, okay? For the reason, this is an interesting challenge here to synchronize these two types of data. And in the research, it's called LiDAR as an understanding. It could be in 3D or 2D. Depends on the kind of sensor of LiDAR here. It could be, for example, 3D. Nowadays, like there are more use cases using 3D LiDAR sensors for the cars. But also, for example, we can work with two-dimensional LiDAR data. So for try to, for example, work in this kind of field, like LiDAR and understanding, we collect different literatures, but I want to focus on this paper. It was very interesting and helpful for our research. Like use for example images, multiple images of the ego car, for try to recognize different objects inside of the point cloud LiDAR data. In this case, they use different models for try to, for example, label this kind of points and try to set a corresponding class for the point cloud data using images. The pipeline is very interesting. It was used for baseline for our pipeline as well. But I will explain more in the next slides. Basically, this is the baseline, and they use, for example, a self-supervised approach for learn this 3D network and get more enhanced representations of this point cloud data. Basically, this is the comparison between our research and this baseline paper. Basically, for example, here we worked with two-dimensional cloud points data, because we worked with a Quasar Interactive Labs digital twin. In our case, we simulate different scenarios of collision in this digital twin environment, and we collect a lot of scenarios for trying a transformer model. In our case, we used a transformer model. In this paper, they used, for example, a convolutional network, 3D networks based on convolutional neural network. And also we work with Essence and no one-to-one images. Basically, we work with sequential batch. It's like a video, for example, of 10 images, in sequence images, to try to capture the more information about the point cloud in this SN. Basically, we used these two type of loss function. It's regions semantic assignment and semantic filtered contrasted loss function for basically for the learning process of the transformer architecture. And also, this is in a pre-trained stage. In the post-training, we used a labeled data. We get from NewSense labeled data for try to improve the representations of this transforming model. Basically, this was the two difference between the baseline and our research. For example, in another pipeline, we use a sum for segment, for example, different objects in the image, and we use, for example, blip2 for get a prompt, a description of each segment in the image. And we used, for example, clip model for get the text representations of the prompt and the image representation using image encoder from clip model. Yeah, and that's basically the pipeline that we used. The principal objective of our research was train a transformer active architecture to design a process to the LiDAR point clouds. The model will convert raw coordinates into RH vector representations. We use 118 dimensions for try to basically represent each cloud point data and try to recognize what object is corresponding to this point cloud. So here I forgot we first for clean the noise points here, we clustered this code points data. For example, we experiment with different key values like 14, 16, 18, to try to reduce the dimensions of the clones points data. We implement a self-supervised pre-training framework using image and text to generate pseudo labels. Basically, we generate pseudo labels using the image, the corresponding image, for trying to train the model. So, and also we validate the pre-trained model by fine-tuning it using a labeled data. In our case, we get data from a NewSense database. That's it. It is labeled cloud points data, and we basically fine-tune our pre-trained model with this data to recognize different objects, like cars, persons, or buildings, etc. So the methodology, basically the framework in general was here. We pretend a model, the transformer model, using different essence collected from Quantum Interactive Labs digital environment. And after that, we fine-tune the model using a labeled data from NewSense dataset, and try to recognize or identify, for example, cars, tree, and objects. Okay. Here, for example, to be honest, we focused in identifying cars because we want to recognize cars, for example, in the ascent for trying to train a model for avoid the collisions. But obviously, it will work good with another kind of objects like a tree objects or pedestrians, etc. So for training loss, the traditional contrastive loss basically works like, for example, we have a centroid of cloud point data here corresponding to this car. In this case, for example, we segment the image, the input image using some model. And basically some model gets different parts of the object very detailed. For example, here we have car, but we have segments of the car, for example, split it in this way. In this case, for example, this point could be assigned to this section of the car, but for example, this section is also corresponding to the car. But in the traditional contrastive loss, it will be set as a different object. Okay, so for semantic filtered contrastive loss, the interesting approach here is like using the prompt get with blip2, for example, model. We can join these different parts of the cars in just one. For example, similar to this figure. Like it's very helpful for set a pseudo label for this point, for example, to entitle the card and not independently with the part of the card, for example. And the negative values is the same for another objects here. So this basically is for try to avoid the negative false issues for different objects inside this LiDAR code please data. So basically, mathematically, it will be represented this way. It's get it from the paper, the baseline paper that I just mentioned. Basically, we tried to adapt this contrastive semantic filter contrastive loss to our research. Yeah. So for the fine-tuning process, basically we got the labeled data as I mentioned from NewSense. There's another one, for example, semantic kitty dataset is another so very useful in this area datasets to try to build this kind of models. Like in our case, we wanted to like fine tune or try to use our pre-trained model to in a real world scenario and to measure what happened in this case, for example. Like basically we worked as a nuisance dataset have in around 16 classes, but we worked with just 4 classes here because as I mentioned, our research focused to identify cars, for example, for train the models for avoid collisions, for example. And for the reason, we just choose 4 classes. In this case, for example, wall, person, car, tree. Like, yeah, but basically, this is the fine-tuning process. And here, for example, the results, the qualitative results that we got it here. It's, for example, this is in a Quantum Interactive Labs scenario. Basically, we can identify different objects inside here. But as I mentioned, we focused on the cars. And for example, we get here, we can measure more accurate the distance using LiDAR data inside this here, for example, after we identify the object. For try to train, for example, another model for avoid collisions. So it's another example, and this is we experiment in different scenarios here in this simulator. And for example, in USN's dataset, first we get a three-dimensional cloud points data and project in 2 dimensions. We clustered first. First to pass to the model with clusters to reduce the noises between these points and try to identify objects inside here. We worked just with, as I mentioned, for example, here we have 3 classes, car, building, vegetation, but we can work with more objects here as well. Yeah, so the application here is basically, as I mentioned, to train a different model to avoid collisions, for predict collisions first. And for example, if you have here the LiDAR data from the ego car, the first stage is identify which of these objects corresponds to these clone points, these centroids. Sorry. So for example, identify here a car using a LiDAR point transformer model. And in the second stage is measure the distance between the ego car to this object. So after that, we trained another model, an LSTM model, to predict a collision using this distance. Before this research, we used just using the image data, for example, using YOLO model to recognize the object and measure the distance between the cars. In this case, we wanted to improve that using a LiDAR data, a LiDAR distance, for try to improve the accuracy of the collision prediction model. So this is another research that was developed to using this data, but basically here the scope was try to recognize or identify objects inside this LiDAR points data. Yeah, we compared with different approaches for our LiDAR point transformer. Basically, another approach is work with 3D cloud points data. That could be more computational expensive because compute 3D-dimensional data will be more expensive. So another difference is, for example, a 3D architecture. Another research use, for example, a -QNet, a convolutional neural networks, on another different architectures. In our case, we used a transformer model because we worked with a sequential data. With sequence of 10 images, for example, and try to get temporal representation in this for each of this design. That's the reason we used a transformer model, because it's useful for represent and temporal information more better. And also we use, for example, a pseudo labels for try to label it as centroids of the point cloud data using image data. We use, for example, clip for do that, and we use also another pre-trained models such as, for example, SAM, DOS, and etc. Yeah, so our model basically was trained with 0.5 millions of parameters, and another models is more, they have a lot of more parameters. And the results, for example, on fine-tuning process using just 1% of label data from UNICAMP, for example, we can we got more accurate to recognize, for example, cars, for recognize pedestrians, vegetations, and walls. For example, in our case, just work with, as I mentioned, for classes, but we can, yeah, for sure, trying to experiment with other classes as well. Like our focus here, as I mentioned, again, is just for cars, because that was our objectives, that try to recognize the cars inside the LiDAR data and try to measure the distance. Okay, so and we wanted to measure as well the power consumptions in the inference process. And here, for example, we use this formula. Basically, we wanted to measure the estimated energy cost using our approach. The parameters that we considered here was a hardware efficiency coefficient. We used 8 Quadro NVIDIA RTX GPU, 8 F8 of this GPU for train our model. And another parameter is the number of input elements. Here, for example, the number of inputs is depend of the number of clusters that we considered. For example, we experimented that with 14, 18, and 19 centroids for reduce the noise of the LiDAR data. And the number of trainable parameters as well of the transformer architecture and the computational complexity. It depends, because, for example, if you work with transformer architecture in the layer of attention, for example, it's basically it could be more complex than a convolutional neural network, but we reduce that using, for example, here the minimum number of input elements. Okay, we don't use, for example, all of the points of the later data. We just use the centroids. And yeah, and that's basically the results of the comparison in the inference stage using our approach. And yeah, that's all. Basically, we submit this research project in here in Simsonium of Brazil in computing. It's interesting conference here, but it's under review right now. But basically here I wanted to share the research that I was developed, as I mentioned, during my internship in Canada. And yeah, I'm open to if you have any questions or thoughts as well.
Yeah, thank you, Luis, for such an amazing presentation. I definitely learned a lot. I think it's like a very timely topic right now, especially we're seeing all these like self-driving cars and all these considerations about like ethics and understanding all our sensors and everything. So I'd like to open the floor to questions. Does anyone have any questions they'd like to ask about the presentation today, or about or it could also be questions about your path as a researcher as well. The floor is open right now. I'll ask a question myself. What kind of work did you do into the ethical side of everything? Did you have to consider that at all, or was your presentation or your research more focused on kind of more the mathematical machine learning aspects? Because I remember when I was learning about kind of the self-driving vehicles, there was also like big like philosophical and ethical questions were asked as well.
Yeah, basically our research focused on the applications. Because, for example, here we just got the contrastive loss from the baseline project here, but the motivation of the project was recognize that the objects inside the LiDAR data, and that's the reason we focus on the applications themselves. Yeah, but the formulation of the maths here is it's basically in the contrastive log there. Yeah, but it was the focus of the project. Yeah.
Oh, that's amazing. I can definitely see lots of work went into this project, and yeah, I'm excited to see where it's heading. So what are your kind of main next steps as like a researcher right now? Are you continuing this project, or do you have any new projects on the horizon for yourself?
Yeah, yes, the principal another motivation is try to, for example, carry this project in a distributed training. For example, the LiDAR data, the image data, it's very sensitive data of the cars. And we tried to train this kind of model in a federated learning scenario, for example, for preserving the privacy of this kind of data. And for this reason, we have to optimize, for example, the transformer model, because the cars, not all of the cars have enough computational resources to train this kind of models, for example. Right. Yeah, and nowadays we are working in federate this training in a distributed way. Yeah, we worked a lot in this approach right now.
No, that's amazing. Thank you so much for sharing. Before we close it out today, does anyone else have any questions or comments?
Like I had a quick question regarding the technical aspect of the place within the pipeline where you have used SAM. So I was wondering, like, does the object properties, like I think so you have used their SAM there to detect or segment those particular objects such that you have like kind of it's kind of easy to find the distances and segment everything else in the for later in the pipeline. So like, is it fast enough in the the path that you follow, or like did you have to experiment with other models like SAM to reach that?
Yeah, thank you for your question. It's very interesting question. We didn't experiment with another models, we just worked with some. Basically, the pseudo label process was in another stage of training process. Yeah, but as you mentioned, it will be time time expensive, right? To process some of this data. Yeah, for sure. Also, for example, we used another model in this pipeline, click, for example, for try to get a prompt for each section. And another pipeline is like, for example, join. For example, some segments different parts of just one object, and we have to join all of that. And we use the prompts, for example, and the cosine similarity of the prompts for try to join these different parts in the defined classes, for example, for the assign the pseudo labels here. Like it will be, as you mentioned, time expensive. That's the reason we did it in another pipeline, not in a training process. Yeah.
So, like, did you experiment this on the Calra or the NVIDIA's simulator, or like something like that?
Yeah, this digital twin, we have the Quasar cars. They have a Jetson NVIDIA GPUs.
Okay.
Yeah, but I like our right, as I mentioned to Katrina, our research is trying to optimize this pipeline because it will be so expensive to train and to run in this GPU with limited resources.
Yes.
And yeah, but we experiment that in a real scenario lab with the cars using a Jetson GPUs there. Yeah.
Okay, cool. So like you had like VML2 scene, like text LiDAR learning with foundation models. Did you also like go to the paths of the trajectories, or like trying to map the trajectories, or as Katrina also jumped in with the query of the like, I will put in a scenario like, if you have a standing vehicle versus some old woman who's trying to cross the road, and you are at a speed, so and you need to slow down, but you can't. So you have to hit something to stop. So like you will choose the standing vehicle. So like those kind of queries, did that came into your like research direction while you were planning?
Yeah. As I mentioned, that our motivation was just for detect cars, for example, for another project that was developed. But yeah, for sure, we also work, for example, with peoples. The different for pedestrian is the pedestrians physically is more small than the cars, and it could be more a little bit difficult to, for example, to recognize pedestrians and differentiate, for example, pedestrians with objects like of different objects in the car in the street, for example. Yeah, but for sure, it will be an interesting another direction for trying a model and try to detect, for example, pedestrians. Yeah.
Yep. Okay. Cool.
Yeah.
Thanks.
No, thank you. Questions.
Yeah, so we have Kevin has a question. Please go ahead. Or Kelvin, sorry.
Hi, thanks for the presentation. It was very interesting. I joined a little bit late, so maybe I missed, maybe you may have answered this question during the introduction of your research proposal. What I wanted to know is that in the development of these multimodal models, how do you like link the gap between like a theoretical framework where you want to be able to basically perform some kind of distributed global training, and how do you link the gap between the framework and actually like deploying them and running them on real cars? Is that an opportunity that you have been afforded?
Yeah. Thank you, Calvin, for your question. It's another interesting question. I think there are a lot of opportunities in research here, because as you know, like the cars and this kind of devices or objects. I told devices. It's limited in terms of computation, for example, and as well in a networking. Like as I mentioned, for example, we tried to train right now this model, for example, in a distributed way using federated learning, for example. And here the principal gaps is the computational resources, which is the cars. It's not enough, the computational resources of the cars right now for trying this kind of models in real time, and for detect or for try to deploy this kind of models right now. So another thing is, for example, the communication overhead that we have to work, for example, in a training process. Because, for example, in a federated learning scenario, basically this model, we have to train this model using different cars, and these different cars have to collaborate and try to deploy for each iteration training to a central server, for example, to aggregation process. And for do that, if the model have a large number of parameters, it will be for example, drop in a computational overhead problem. And for the reason, for example, we can use right now LoRa, for example, for just trying a minimal parts of the model, or get, for example, a pre-training model and try to just adjust a percent of parameters, the model, etc. There are different ways to do that, but yeah, there are a lot of opportunities here in this kind of scenarios, using, for example, a foundation models or models which have a large number of parameters, such as transformer, for example.
All right. I have a follow-up regarding the like physical platforms that you can use, but maybe we can connect after and discuss that. But thank you.
Yeah, thank you.
Were there any more questions that are in the queue? I don't see any more hands raised. Anyone else?
No, yeah. If you want, like, we're basically, my research project is try to carry this kind of centralized training model to a federated process, in a distributed process, training process. And yeah, if you were interested in like continuing this kind of research, you can contact me, and it's like great for me to follow research in this area. And that's all. Yeah, thank you, Katrina, for your invitation again. And yes, I think that's all.
No, thank you so much. We learned so much from your presentation, and yeah, thanks for your contact information. We'll definitely be sure to keep you in keep in touch if we have any further questions. And yeah, with that, on behalf of Machine Learning Math and Cohere Labs, we thank you so much for coming, and we look forward to hearing from all of you in our community. So Have a wonderful day, everyone.
See you. See you guys. Thank you.